In this video, we're going to look at power series and functions. We're going to identify a power series and provide some examples of power series. We're going to determine the radius of convergence and the interval of convergence of a power series, and we're going to use power series to represent a function. A power series is a special type of series with terms that involved variables. So unlike before, our series typically had numbers. More specifically, the variable that we will use is x, and then all the terms of the series involve powers of x. And as a result, a power series can be thought of as an infinite polynomial. And just as a refresher, what does it mean to be convergent or the series converges? That means that as we add terms to it, as we get out there as n goes to infinity, that it no longer changes the sum for each number that I add to it. Every partial sum gets to a point where every term after I add to it is so small that it doesn't actually change in any significant way the value of the partial sum. And as n goes to infinity, a sub n goes to 0, as an example. A divergent series is an infinite series that is not convergent, meaning the infinite sequence of the partial sums of the series does not have a finite limit. So here's an example of what a power series look like. We have n equals 0 to infinity. We have some constant sub n, and we have x raised to the n. So our first one would be a constant, so c naught plus c1x plus c2x, etc., where the variable is x and the coefficients are constant c sub n, and we know this as a power series. So 1 plus x squares, and it continues on up, where my constant is just 1. This is an example of a power series. Since this series is a geometric series with a ratio of x, because this is how we would have defined a geometric series. Actually, the way we would have defined a geometric series before is we would have said the summation of n equals 1 to infinity of x to the n minus 1. And then all we do to move the index down to 0 is we add 1 to this. And so we end up with you can see, a geometric series where the ratio is x. We know that it converges when this value x is less than 1 and diverges when this value, absolute value of this x is greater than or equal to 1, because that's a geometric series. So here how we are going to formally define a power series. N equals 0 to infinity of c sub n x to the n, and it starts out with a constant plus c1x, c2x squared, and it continues. A power series is centered at 0 in this case, and if it is not centered at 0, it will have this form, n equals 0 to infinity of c sub n x minus a raised to the n, which is equal to c naught plus c1 x minus a plus c2 x minus a squared, and etc. And to make this definition that we have precise, we're going to stipulate that x raised to the 0 is 1, and x minus a raised to the 0 is 1, even though when x is equal to 0 and x is equal to a respectively. So normally we would have x 0 raised to the 0 as a problem, but here we're going to just say x raised to the 0 is 1 and x minus a raised to the 0 is 1. Here's some examples in which the first two examples I'm centered at 0, and I know I'm centered at 0 because I don't have an x minus or x plus raised to an n. And then to determine what my a sub n is, in this case it's 1 over, so this is my a sub n. For this one, my a sub n is 1 over n factorial. For this is my a sub n, c. We're using c here, so I'll be consistent and I will use c sub n, and c sub n is equal to n factorial. Since this is 1 over, all of this is my c sub n, and this one is centered at 2 because I have the structure of x minus the a raised to the n, x minus a raised to the n, so this is centered at 2. Now, since the terms in a power series involves a variable x, the series may converge for certain values of x and diverge for certain values of x. For a power series centered at x equals a, the value of the series x equals a is given by c naught. Therefore, a power series always converges at its center. Some power series converge only at that value of x. Most power series, however, converge for more than one value of x. In that case, the power series either converges for all real numbers x or converges for all numbers x in a finite interval. So we consider this power series n equals 0 to infinity. This is a theorem, c sub n, x minus a to the n, is a series that satisfies exactly one of the following properties. It converges at x equals a and diverges everywhere else, so it converges at its center. The series converges all the time no matter what we choose for x. Or there exists some number r in such that the series converges at x minus a less than r. And we're going to call this radius of convergence. And for all values where x, the absolute value of x minus a is equal to r, we have to check those endpoints. And the series converge or diverge. So this gives us our interval of convergence. So either it only converges at the center, converges for whatever number we choose for x, or it converges for an interval, and then we have to check the endpoints of that interval to see whether or not it converges at the endpoints of the interval. So if a series falls into case 3, the convergence of the power series, then the series converges for all x. So in other words, it's just saying, hey, we have to check to make sure this is going to work or not. So consider this power series, the set of real numbers x. The series converges an interval of convergence. Then there exists some number big R greater than 0. So the series converges. R is the radius of convergence. It's saying a whole bunch of stuff to say this is R is the radius of convergence. If the series converges at only x is equal to a, we say the radius of convergence is 0. And if the series converges for all real numbers, we say the radius of convergence is infinity. So here are our examples. So here it converges only at a. This is only at a, so this is case 1 of our theorem. Case 2, it converges all the time. And case 3, it only converges some distance r, the radius of convergence, away from my center, and it diverges everywhere else. So the figure that we have up above shows the radius of convergence at different places. That's what I showed you up above. Now we're going to determine if this statement is true or false. For the first one here, n equals 1 to infinity of a sub n x to the n. We're going to see if it converges at x for any real number. And this one's not too bad. All we have to do then is do the summation of n equals 1 to infinity of a sub n 0 to the n. And you can see as I start writing this out, I'm going to get a sub 1 to the 0 plus a sub 2 to the 0, a sub 2 times 0, I should say, and then a sub 3 times 0, and no matter what we get is we get 0. And you're wondering why we started at 1. Well, so we can't start at 0 because it would be 0 raised to the 0. And so I'm checking for convergence at x equals 0. So I'm going to start at n equals 1. So this is true. True. The second one, if n equals 1 to infinity of a sub n x to the n has a radius of convergence that is greater than 0, and if the absolute value of b sub n is less than a sub n for all n, then the radius of convergence of b sub n x to the n is greater than or equal to my radius of convergence for my a sub n x to the n. This one is also true. Notice that b sub n, the absolute value of b sub n is less than or equal to a sub n. So that tells me that b sub n over a sub n has to be less than or equal to 1 because a sub n would be larger. And since that's true, then the radius of b sub n must be greater than or equal to the radius of r. So this one is also true. Now, if you remember from before, we had a power series, and we usually use the ratio test. So let n equal 1 to infinity of a sub n be a series with non-zero terms. Again, this is what we did from before. Rho is equal to the limit as n goes to infinity of a sub n plus 1 over a of a sub n. Then we have all of this stuff that we did from before in chapter 5. And we're going to use that more than anything else when we're trying to find the radius of convergence for each series. So for me to do A and B, I need a little information because I don't have any way to relate a sub n to a sub n plus 1. So let's just assume it's going to be in the homework. It's probably in the book. And I probably just dropped it. A sub n plus 1 over a sub n. The absolute value, the limit of this as n runs to infinity. Let's have this as 1. I think I'm missing that notation in this, or I'm missing that bit of information to be able to do A and B. I don't need the information for the other ones because I actually have an A sub n, but I will need it for 1 and 2. So we're going to start with the root test. And so we do the limit as n goes to infinity. And we have a sub n plus 1, 2 to the n plus 1, x to the n plus 1, over a to the n, 2 to the n, x to the n, absolute value. Now this is the same thing as the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, multiplied by the limit as n goes to infinity. Now these are limit laws that allow me to do this. And I can see that 2 to the n plus 1 will be positive, 2 to the n will be positive. I don't know anything about x, so I probably should keep those in absolute values at least initially. So I'm going to write this as 2 to the n times 2, x to the n times x to the 1, 2 to the n, x to the n. Now this goes to 1 because I have to know this information, otherwise I wouldn't be able to do this problem. My 2 to the n's cancel, my x to the n's cancel, and what I end up with then is you can see all of my dependence on n's are gone, and I'm just going to get 2 multiplied by x, and it's the absolute value. For this to converge, the absolute value of 2x has to be strictly less than 1. Now, if I write this as a compound inequality, I get negative 1 is less than 2x, which is less than 1. Dividing everything by 2, I get negative 1/2, which is less than x, which is less than 1/2. So what I have is my radius of convergence, my big R, is equal to 1/2. Now, if I'm only asked for the radius of convergence, I'm done. So here's my answer. What I don't know without doing some more work is whether my interval is going to go from negative 1/2 to 1/2. If it's going to go from negative 1/2 to 1/2, where one side is included and the other side isn't. So these are my choices. I could have inclusive on both ends. I could have inclusive on one and not on the other. I could have inclusive on this side, negative 1/2, and not on the positive 1/2. Or I can have non-inclusive on both sides. So these are the possible things that could happen for my interval of convergence. And I won't know that until I test it, and I will be doing it later. I'm just not doing it in this part. The only part I needed is the radius of convergence, and so I've answered it. These will be answered later in the video. All right, so same kind of thing here is we're going to do the limit as n goes to infinity of the absolute value of a sub n plus 1, negative 1 to the n plus 1, x to the n plus 1, 10 to the n plus 1, multiplied by the reciprocal, so 10 to the n over a to the n, negative 1 to the n, and x to the n. This gives me the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, multiplied by the limit as n goes to infinity. Now I'm going to go ahead and cancel stuff before I write what's left over. So this is 10 to the n, 10 to the 1. This is negative 1 to the n, negative 1 to the 1. This is x to the n, x to the 1. So this 10 to the n and that 10 to the n cancel. The negative 1 to the n and that negative 1 cancel. The x to the n and x to the n cancel. So in the numerator, I'm left with the absolute value of negative 1x over just 10. Now, this is no longer dependent on n. Since this portion goes to 1, this is just going to be the absolute value of x over 10. Now, you noticed that I did not write negative 1. Well, that's because it is negative 1 times x, and the absolute value of negative 1 is 1. And similarly, we're going to do x over 10 is going to be absolute value is less than 1 for it to converge. So negative 1, the less than x over 10, which is less than 1. So I get negative 10 is less than x, which is less than 10. So my radius of convergence, you can see, is 10. Okay, so now on C, we're going to be doing a little bit extra because I now have a C sub n. So this part is my C sub n, my A sub n if you want, or C sub n. Because that's my A sub n or C sub n, I do have to do the limit now as n goes to infinity. Absolute value of n plus 1 multiplied by x to the n plus 1 over e to the n plus 1 multiplied by its reciprocal. So I'm going to have e to the n over n x to the n. We know this is x to the n multiplied by x to the 1. This is e to the n multiplied by e. Canceling my x to the n's, I'm going to cancel my e to the n's. And what I'm left with is the limit as n goes to infinity. I'm going to have n plus 1 multiplied by x in the numerator, and in the denominator, I'm going to have en. E multiplied by n, that's not e raised to the n. Now, as before, if I divide the numerator by n and the denominator by n within the absolute values, I'm going to get the limit as n goes to infinity of x multiplied by 1 plus 1 over n over e. Now as n runs to infinity, this is going to go to 0, so I'm going to get the absolute value of x over e. And so you know from here, at this point, you know the radius of convergence is going to be e. Let's take a look at D. So the limit as n goes to infinity of 2 to the n plus 1 factorial x to the n plus 1 n plus 1 raised to the 2n plus 1 multiplied by n raised to the 2n over 2 to the n factorial x to the n, all inside the absolute values. So let's do some algebra over here. This is 2 to the n plus 2, just distributing, 2 to the n plus 1, and then 2 to the n factorial. I have x to the n. I'm going to have n plus 1 raised to the 2n, and then multiplied by n plus 1 raised to the 2. Again, distributing, this is 2n plus 2. This is going to be multiplied by n raised to the 2n over 2n factorial x to the n. Let me see, 2n factorial will cancel. X to the n cancels. All right. So this is going to be equal to the limit as n goes to infinity of 2 to the n plus 2 and that should be absolute value. Change that to absolute value. 2n plus 1 over n plus 1 squared. And again, I said absolute value, and I put a curve there, so absolute value. I'm going to have an x left over. But you're like, wait a minute, isn't there an n raised to the 2n, and isn't there an n plus 1 raised to the 2n? There absolutely is. So this is times n raised to the 2n over n plus 1 raised to the 2n, absolute value. This is going to be the limit as n goes to infinity of the absolute value of 2n plus 2 multiplied by 2n plus 1 all over n plus 1, the quantity squared. This x is not dependent on anything, so I can factor that out in front of the limit. So let me erase this. So I can write this as the absolute value of x multiplied by the limit. Now, this portion looks super familiar. We've done that a couple of times. So this is going to be the limit as n goes to infinity, so this is the multiplication here, of n over n plus 1 raised to the 2n, still in absolute values. And we know we do that y equals the n over n plus 1 shenanigation raised to the 2n. We take the natural log of y, we get n, the natural log of n over n plus 1, and all that crap. We're like really familiar with that. Now, similarly, here we're also familiar with this. We're going to have 2n squared times 2n, so that's going to be 4n squared. So 4n squared plus 6n plus 1 in the numerator. The denominator, going to get n squared plus 2n plus 1. So this is going to be equal to the absolute value of x, the limit as n goes to infinity of, if I divide this numerator by n squared, I divide this denominator by n squared, I'm going to get 4 plus 6 over n plus 1 over n squared. I'm going to get 1 plus 2 over n plus 1 over n squared. And then when I do my usual, doing the limit of this thing, I'm going to get e raised to the negative 2. And as n runs to infinity on this grouping, this limit grouping, I'm going to have all of those go to 0. So when I get done, I'm going to get the absolute value of x multiplied by 4 multiplied by e raised to the negative 2. So I'm going to have 4x over e squared is less than 1, which is less than negative, or is greater than negative 1. So I'm going to get e squared over 4 is less than x, which is less than e squared, that should be negative, e squared over 4. So my radius of convergence is e squared over 4. Right, way back over here, so we have this last one, and then we're going to be testing the end points, which is always delicious, scrumptious even. The limit as n goes to infinity, n plus 1 factorial, x to the n plus 1, n plus 1 raised to the n plus 1, multiplied by n to the n over n factorial x to the n, absolute value. That's because this is x to the n over 1, so it needs to be 1 over. As before, we're going to do our algebra, n plus 1, n factorial, x to the n, x to the 1, n plus 1 to the n plus 1 to the 1, n to the n factorial, x to the n. Now let's start canceling stuff as we love to do. N factorials cancels, x to the n's cancels, n plus 1's cancel. So I'm left with the limit as n goes to infinity of the absolute value of x n raised to the n plus 1 raised to the n, which is equal to the absolute value of x, the limit, as n goes to infinity of n raised to the n plus 1 raised to the n. And I'm hoping by this point you're realizing that there's a pattern to this. And you're thinking, man, I've done that enough times. I'm really excited about not doing that again. So what you end up with is the absolute value of x over e. So negative e is less than x, which is less than e. So my radius of convergence is e. And again, we do that shenanigation. Y is equal to n raised to the n over n plus 1 raised to the n. And then you do the natural log and all that stuff. I'm not going to go through it again. What I do know is at this point we have done this enough times that when we see this form, this limit as n goes to infinity of n raised to the n over n plus 1 raised to the n is e raised to the negative 1. I'm not doing it anymore. So, now, if we can represent a series as a polynomial, then we can both differentiate and integrate it. So consider this geometric series. We know that a plus ar squared plus ar to the third converges if and only if the r is less than 1. And in that case, it converges to a over 1 minus r, because that's what it converges to for a geometric series. Therefore, if the absolute value of x is less than 1, the series converges to 1 over 1 minus x, and we can write it like this. We can say 1 plus x squared plus x to the third. We can take this polynomial and write it like a rational function, which means our rational function can be wrote as a power series when the absolute value of x is less than 1. And we know from last chapter what we had as 1 over 1 minus y is equal to the summation of n equals 0 to infinity of y to the n, but now we can use x. And it's going to converge between negative 1 and 1. Find the power series centered at a and identify its interval of convergence. So now I'm going beyond just finding the radius. It's asking for the interval. So that means I'm going to have to check the endpoints. So the first thing I'm going to do is rewrite this in the appropriate form. So the first thing I'm going to do is I want it to look like this. So I'm going to write this as 1 over 1 minus x the quantity squared. Now it's in the proper form. I can write this as n equals 0 to infinity of negative x the quantity squared raised to the n. Now I'm going to rewrite this as the summation of n equals 0 to infinity of negative 1 to the n, x raised to the 2n. And the reason I'm going to do that is because for a power series, I need my variable, or maybe my variable minus number, raised to the power. This negative 1 is a coefficient, so I need to break it apart. So this is where I am. Once I get to this point, my second step now is to do my limit. So this is the first step. My second step is to do the limit as n goes to infinity of this series, which is the absolute value of negative 1 raised to the n plus 1, x to the 2 n plus 1, over negative 1 raised to the n, x raised to the 2n, absolute value. This is going to be the limit as n goes to infinity. This is negative 1 to the n, negative 1 to the 1, x to the 2n, x to the 2, all over negative 1 to the n, x to the 2n. These cancel, and I'm going to be left with the absolute value of negative 1 x squared, which now I have the absolute value of negative 1 is 1, so I have the absolute value of x squared. And so we have the absolute value of x squared is less than 1. And that's going to be true if and only if, double arrows mean if and only if, the absolute value of x is less than 1. And therefore my radius of convergence is 1. Now I have to check to see whether or not I'm going to have negative 1 to 1, non-inclusive, negative 1 to 1, inclusive, etc. So with this, I'm going to go back to here, and x is going to be 1 and x is going to be negative 1. So these are my two endpoints. So I'm going to go back and say the summation of n equals 1 to infinity of negative 1. I'm going to check the left endpoint, so I'm going to check negative 1 to the 2n. Well, this is just going to be the series as n equals 1 to, or excuse me, these should be 0, 0 to infinity of, well, this is going to be negative 1. This is going to be negative 1 squared raised to the n, which is just the summation of n equals 0 to infinity of negative 1, 1 to the n, which diverges. That means negative 1 is not included. Similarly, I'm going to do the same thing for the summation of n equals 0 to infinity of negative 1, checking the other endpoint, which is 1 raised to the 2n, which is, again, just the summation of n equals 0 to infinity of negative 1 times 1 to the n, which also diverges. So my interval of convergence, my final answer is negative 1 to 1. These are not included. All right, let's take a look at B. I'm going to rewrite this as x squared multiplied by 1 over 1 minus a minus x squared. So it's in the appropriate form. So we have the summation, x squared out front, of n equals 0 to infinity of negative x squared raised to the n. So this is going to be equal to the summation of n equals 0 to infinity of negative 1. And that should be an n. I said n and I wrote 2, so that's pretty cool. This is going to be negative 1 raised to the n and x raised to the 2n. And then since I brought in that other x, I'm going to have, or x squared, I'm going to have x squared. So this is going to be the summation of n equals 0 to infinity of negative 1 to the n, x raised to the n plus 1 times 2. I think I might just leave it as 2n plus 2. Now I'm ready to do the limit as n goes to infinity of negative 1 to the n plus 1, x to the 2n plus 1 plus 2 over negative 1 to the n, x to the 2n plus 2, absolute value. The algebra that's going on is negative 1 to the n, negative 1 to the 1, x to the 2n plus 2 times x squared over negative 1 to the n, x to the 2n plus 2. Those cancel, and I'm going to get the limit as n goes to infinity of the absolute value of negative 1 to the 1, x squared. Oh, well, what do you think about that? That's not anything different than what we just did. So since we already did this, we ended up with the exact same thing as we did up here. We know our radius of convergence is 1 and my interval of convergence is negative 1 to 1. So there's my answer. And here's our last one. So here we go. This is going to rewrite this as x squared. 1 over 1 minus 4x squared. So this is going to be x squared, the summation of n equals 0 to infinity of 4x squared raised to the n, which is equal to the summation of n equals 0 to infinity of 4 to the n x raised to the 2n plus 2 by bringing this x squared in. So now I'm ready to do the limit. So the limit, as n goes to infinity, of 4 to the n plus 1, x to the 2n plus 2 plus 2, over 4 to the n, x to the n plus 2 plus 2. And you can see this is going to become the limit as n goes to infinity. I'm going to be left with a 4. I'm going to be left with an x squared. That's about it. So the absolute value of x squared has to be less than 1. And that's going to be true if and only if 2x, the absolute value is less than 1. So my radius of convergence is going to be 1/2. Now, if I go back and do my testing once again, I'm going to put x as being 1/2. I'm going to have the summation of n equals 0 to infinity of, I'm putting the r in here. So I'm going to have 4 raised to the n. I'm going to have 1/2 raised to the 2n plus 2. And this is going to be n equals 0 to infinity. Actually, I should have done the negative first, but I'm going to do the positive first. I'm going to get 4 to the n. I'm going to rewrite this as 1/2 to the 2n multiplied by 1/2 squared. This is the summation of n equals 0 to infinity of 4 to the n. This is going to be 1 over 4 raised to the n. And the reason this worked out, let me backtrack. If I have 1/2 raised to the 2n, this is 1 over 2 squared raised to the n, which gives me 1 squared over 2 squared raised to the n, which is 1 over 2 squared, which is 4. 4 raised to the n, which is just 1 over 4 to the n. Okay, so let's go back to where we were. I still have the 1/2 squared. You can see that these cancel, and what I'm doing is I'm doing a summation of 1/2, the quantity squared, and we know when we're doing summations of constants, it's just going to be the 1/2, the constant, multiplied by the upper limit. So I have 1/2 raised, around 1/2 squared times infinity, which is obviously infinity. So the 1/2 will not be included on the interval. So I get 1/2. I'm going to not include that. And then putting in a negative 1/2 here, because this is squared, isn't going to change anything. So the 1/2 isn't included as well, is not included as well. And that's it for this video.